Let's do some more examples of sketching the graph of a function using all of our techniques from Chapter 3. We're going to start off looking at problem 18. Here we have a function, y is equal to x to the 5/3 power minus 5 times x to the 2/3 power. So kind of an interesting function here. Might not be exactly what you expect. And we really don't even have too much of an idea exactly what's going on with this thing. Now we can talk about the domain right away. What is the domain of this function? What numbers make sense to be plugged in here? Well, note here that the powers of 5/3 and 2/3 are both positive. And neither of the denominators here, this 3, is even. That means we're not dealing with any even roots. There's no square roots, there's no fourth roots. In fact, we're dealing with a cube root with some additional, like this is the square of the cube root. This is the 5th power of the cube root. But the point here is that this function is in fact defined for all real numbers. No matter what real number I plug in, I can take its cube root and then I can square that number. And nothing here is on the bottom. We don't have a negative exponent here. Same thing with the 5/3 power. So our domain is actually all real numbers. This also doesn't have a horizontal asymptote because, well, that's not really so obvious. But what we can think about is if we let this thing go off to infinity, if we let the x go off to infinity in here, the higher power is always going to dominate this function. This x to the 5/3 is going to take over. And as x goes to positive infinity, this thing actually is going to go to infinity. Same thing if we go to negative infinity. This x to the 5/3 is still going to be the most dominant part of the function, and this part, as we go to negative infinity, goes to negative infinity too. Because we don't have an even number here. This 5 is not going to make things positive. So actually, there's this is defined everywhere, and it's actually going to go from negative infinity on the negative infinity side to positive infinity on the positive infinity side. In fact, that kind of even implies already that our range here is all real numbers. Let's go ahead and make a number line for the function itself. So we're asking, where is our function equal to 0? Well, our function was x to the 5/3 minus 5x to the 2/3. How do we find where this equals 0? Well, what we can do is actually we can pull out this x to the 2/3 power. I'm going to pull that out of this thing. That's definitely going to just leave a minus 5 back here. If I pull an x to the 2/3 out of x to the 5/3, I essentially just subtract 2/3 from 5/3. 5/3 minus 2/3 is a 3/3, or just a power of 1. There's a reason why they chose these particular ones. 5/3 is 1 more than 2/3. And so we get a very nice x to the 2/3 times x minus 5 that we're setting equal to 0. Well, if x to the 2/3 equals 0, then x is 0. If x minus 5 is equal to 0, then x is 5. Those are the two places our function equals 0. Go ahead and make a number line for that. Of course, we do need to find out what are the values of the function on test points. So from negative infinity to 0, just go ahead and pick -1 for that. If I plug -1 into my function, well, -1 to the 5/3 is actually a -1. Remember there, the 5 being an odd number here means that we do actually just get to bring the negatives along. But in here, x to the 2/3, the 2 actually gets rid of the negative. So really, this is -5 times a positive 1. -1 minus 5 is a -6. We get a negative number. If we plug in 1 instead, this time we just replace our our powers here with 1s. We have 1 minus a 5, which is still negative. It's -4 this time. But then after 5, now we could go ahead and pick 6 and plug it in. Unfortunately, because we are dealing with these fractional exponents, that can be a little bit tricky to do. Just plug in 6. You could do it with a calculator pretty easily. I'm actually going to pick the next test point to be a cube, because when I'm taking the cube root, that's actually going to work out pretty nicely. The next cube after 5 is 8. That's 2 cubed. If I take 8 to the 5/3, well, I'm going to take the cube root of 8 to get a 2, and then 2 to the 5th power is a 32. Here, I still have the minus 5, but now I have 8 to the 2/3. Well, I'm going to take the cube root of 8 to get a 2, and then 2 to the 2nd power is 4. So 32 minus 5 times 4, or 32 minus 20, gives me a 12. Specifically, a positive 12. So it's negative here, it's still negative here, but now it's positive over here. I should label this. This is specifically for y. If we move on to our first derivative, remember our function here is x to the 5/3 minus 5x to the 2/3. If I take the derivative of that, I use my power rule. Remember that we just bring out the 5/3. We reduce the power of 5/3 by 1. We actually already know that that's going to be 2/3. Over here, we have minus 5 times the 2/3, or in other words, we have a 10/3. Then x to 1 less power. 2/3 minus 1 is now a negative 1/3. We want to see where we have critical points. Specifically, we have 2 questions here. Where is this equal to 0? Or where does this not exist? We'll come back to that in a moment. But let's see what happens when this equals 0. Now this looks a little bit complicated, but it's not really that bad. For one thing, we can pull out the third part of it. And we could also pull out a 5. And actually take 5/3 from this. That's just going to leave a minus 2 on this part. And I'm also going to go ahead and pull out an x to the negative 1/3. I'm going to put that here. That's just going to leave me with only a negative 2 on this last term. On the first term, I'm going to take 2/3, and then I'm going to subtract a negative 1/3. That means I'm adding 1/3 to 2/3, which also gives me an x. Essentially, the fact that x to the minus 1/3 is 1 less power than x to the 2/3, which is what we got from our derivative, or where we got the negative 1/3 from our derivative of 2/3. That's just going to leave me with an x here. Now, this is going to equal 0 when x equals 2, of course. Now, this part here is not going to ever equal 0, unlike what we had before. We do not get 0 like we had for the x to the 2/3. X to the negative 1/3 is actually an x, the cube root of x on the bottom. So this is never going to equal 0. But it will not exist when x equals 0. So x equals 2 is a place where the derivative is 0. The derivative doesn't exist when x equals 0. So 0 is still going to be on our number line. 0 here, we have a 2 here for our first derivative. Of course, we need to go ahead and take our test points. We'll look at the first derivative at 1, or let's say negative 1, 1, and I think I want to take 8 again, just because we are dealing with all these cube roots still. 1 and negative 1 are very nice when it comes to cube roots anyways. Alright, so we have 5/3 times negative 1 to the 2/3. Well, the 2 there means we actually have a positive 1, so we have a 5/3. Here we have a 10/3 times negative 1 to the negative 1/3. Because we don't have an even number here, we are actually going to keep that negative. Negative 1 to the negative 1/3 is actually a negative 1. So we're getting to add 10/3. In other words, we're going to get 15/3 or 5 for our first derivative at negative 1. It's a positive number. When we plug in 1, well, this is actually even easier. All our powers just become 1. We have a 5/3 minus a 10/3. In other words, a negative 5/3. We have a negative number. Finally, at 8, here we have 8 to the 2/3. We take the cube root of 8 to get a 2, but then we square it to get a 4. So we have 5/3 times 4 minus a 10/3. Now we have to figure out what 8 to the negative 1/3 actually is. Well, keep in mind this. We take the cube root of 8 to get a 2. 2 to the negative 1 power is actually a 1/2. Remember that negative power means that we flip it upside down. So this is 20/3 minus 5/3. In other words, we get another 15/3 or 5. Get a positive, a negative, and a positive. Now, at this point, we could make a guess at how it actually goes, but this is a case where actually looking at the second derivatives is actually really important, and we'll see why that is in a moment. What is the second derivative? Now, remember our first derivative. Maybe I should go ahead and actually write out the first derivative here, make it a lot more obvious. Remember, our first derivative was 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. That means our second derivative, if we do the power rule again, this 5/3 gets multiplied by a 2/3. In other words, we get 10/9. One less power from the 2/3 gives me a negative 1/3. Here we get a negative 10/3, but times this negative 1/3. So actually the negative becomes a plus. We still have the 10, but now we have it over 9. And one less from negative 1/3 is negative 4/3. So that is our new power. This is our second derivative. And we're going to ask the same questions about this second derivative. Where is this thing equal to 0? Where does it not exist? So if you set this thing equal to 0, of course, we can pull out a 10/9. I'm also going to pull out that lower power like I've been doing on the previous functions. That's going to just leave me with a plus 1 over here. Over here, when I pull a negative 4/3 out of the negative, if I pull an x to the negative 4/3 out of the x to the negative 1/3, I'm going to be subtracting the negative 4/3 from the negative 1/3. Essentially, I'm taking negative 1/3 plus 4/3, and I'm just going to get an x to the first power again. So very similar to the previous two factorizations that I did back here and back here. But the point here is now this part, because this is on the bottom, does not ever equal 0. The only way this is ever equal to 0 is if x plus 1 equals 0. In other words, x equals negative 1 is my only solution to this being equal to 0. But the derivative does not exist when I put 0 into this thing because it's on the bottom. So it does not exist when x equals 0. So those are 2 points that we're going to have to look at. Our number line for the second derivative is going to include 0 and negative 1. So unlike the previous ones, the other points is actually on the other side of 0. We could align these up if we wanted to, but I'm not too concerned about that. We can go ahead and put in my test points. So from negative infinity to negative 1, I can just go ahead and pick... Actually, probably should pick negative 8. Remember that I'm trying to pick cubes so that I can take my cube roots easier. From negative 1 to 0. Now that one's going to be a little tricky if we're trying to pick numbers that come out very nicely. If I want to pick a nice cube number in there, I think the best one to be picked negative 1/8. because here we're dealing with basically negative 1/2 cubed, and that's going to come out somewhat nicely when I plug it into my formula. Finally, from 0 to infinity, I can just go ahead and pick 1 there. That one's very nice. So putting 1 just makes me get a 10/9 and a 10/9, so a 20/9. For -8, when I plug that in here, so -8 to the -1/3, that's going to, I'm going to cube root the 8 and get a 2. -2 to the -1 is a -1/2. And then here, we saw the 10/9, but I'm going to take -8 to the -4/3. Well, the cube root of 8 is 2. -2 to the -4 is going to actually be a positive 1/16. And then you can kind of tell already we have this 10/9. That's not really going to make too much of a difference because it's multiplying both of these. But the -1/2 plus the 1/16, this is not enough to take a -1/2 to being positive. This result is actually going to be less than 0. If we wanted to work it out, we could. I mean, we could combine those. This would be what? 8 over 6, -8/16. We end up getting a -7/16, but then times 10/9. But we still have a negative, is the point. If I plug in -1/8, well, I'm still going to get the 10/9. I'm going to pull that completely out. I'm going to have 10/9 on both of these, but I want to worry about what are these powers of -1/8. When I take the cube root of -1/8, I actually get a -1/2. But then the -1 power of that is a -2. Then doing the same thing here, we still have the -2, but now it's to the we still have the -1/2, but now it's to the -4 power, which means it's going to be a -2 to the 4th power. The negative goes away, and we're left with a plus 16. In other words, 16 minus 2 is 14 times this positive number, and we get a positive number overall. Exactly what these numbers are is not really too important, but we kind of want to get an idea of how we can find out why they're positive or negative. But note here we have a negative, a positive, and another positive. And those are the important key points here. Note that what this is already saying is that we have an inflection point at -1 because the concavity does change here. We do go from negative to positive, but we actually do not have an inflection point at 0. Even though 0 is a point in our domain, and it's a point where the second derivative equals 0. Or, well, I guess, no, the second derivative doesn't equal 0 there. It doesn't exist there. Now we go ahead and graph these points. So first of all, we have our x-intercepts of 0 and 5. Technically here we also might have wanted to think about the y-intercepts, but because 0 is already an x-intercept, we know what that was. Put this over here. Because I do know that the function is going to be negative all the way from -infinity until it gets to -5, or it gets to positive 5. So it's going to be down here. I'm not going to interfere with these. It's going to go positive after 5. So I want to put this over here. Just trying to line up things so they don't kind of overlap my graph that I'm going to eventually get. Next thing, I do want to graph the critical point. So we already have the one for 0. What happens at 2? If I plug 2 into my original function, well, this one, unfortunately, we're not going to get a very nice number. So y of 2, we're going to have 2 to the 5/3 minus 5 times 2 to the 2/3. And I'm just going to go ahead and write that as negative 3 times the cube root of 4. And you can work that out for yourself, why that's actually the value there, if you want to simplify it. I just want to be able to write down a value. But it is a negative number. It's some point down here. We have the point 2 comma negative 3 cube root of 4. All right, what's next? Well, we also have this inflection point here at negative 1. What is the value at negative 1? In fact, want this to be black. We have y of negative 1. This one's a little nicer than 2 was. Putting negative 1 in here gives me a negative 1. Putting a negative 1 here gives me a positive 1. We have negative 1 minus 5, or negative 6. Or, really, we already found that one. Y of negative 1 was negative 6. But the point is here we have an inflection point of negative 1, negative 6. Negative 6 is actually lower than negative 3 times the cube root of 4. That's approximately negative 4 and some change. So we'll have a point down here. We have an inflection point there. Alright, so exactly what is happening on our graph? Well, note we are concave down until we get to negative 1. We do have a cup shape to this. Cap shape to it. It is something like that. After negative 1, it goes to concave up. Now, that might be a little bit surprising because we know that it has to come up to at 0, 0, and that's going to be a local maximum, or a relative maximum. But it's going to come at it in that kind of a form. It's not a cup shape, or a cap shape here. It does not look like the top of a hill. It actually is going to be kind of a point. It's going to come up like that, and then it's actually going to be, well, it's still going to be concave up, but now it's decreasing and still negative. So it's going to look something like that. If all you did was look at the function in its first derivative, you think, well, it's negative and increase and decrease, and you might think it goes something like, you might think it does something like this, sort of like a negative x squared kind of shape, but it doesn't. It's a very different looking shape. Then our function, well, this time it's still concave up from that point on. It decreases and then increases after 2, and then hits here at 5, 0. This one actually is going to look a little bit more normal. It's going to look something like that. But we have this thing is concave down, but then switches to concave up to make a sharp point at 0, and then does a lot nicer graph after that point. So this is a place where if you didn't take that second derivative, you could trick yourself into thinking it's a very different looking graph than it actually is. Let's go ahead and actually look at this, at what GeoGebra gives us here, and compare our results. So our function is y equals 5x to the 5/3 minus 5x to the 2/3. And we get kind of the shape that we expected. Now, in their particular case, they had the same scale on both these. We should probably expand that out a little bit to kind of match what we had. We had our points of 0, 0. We had a 5, 0. We had a 2, comma. Let's just say f of 2. It'll give us the value. It's about, well, negative 4 and some change, like I said. And then we had negative 1, negative 6. This is the point. This is actually concave down. It's concave down on this part. It's a little hard to tell that just because it's not very concave down. At least not at the part that we can see. But then it switches to concave up. It's not coming at it at the angle we expect to. It comes at it really from below instead of on the side. Then it does this much nicer part over here. That point at 0 is kind of a nasty point for this function. Let's look at one last problem. It's going to be problem... Oops. Did not want to do that. Let's look at problem 14. Here we have y is equal to x squared plus 4x plus 7 divided by x plus 3. This is another rational function. But we want to see exactly what's going on with this thing. First things first, we can look at its domain. Of course, the only place that's not in the domain is going to be when the bottom equals 0, and that's going to be at x equals negative 3. So here, the domain is everything except for negative 3. If we do take negative 3 and put it into our numerator, you kind of have to work that out, but it turns out it does not give us a 0. So we do actually, in fact, have a vertical asymptote of x equals negative 3. However, since the top is bigger in degree, if the top has a degree of 2, the bottom has a degree of 1, the top's degree is bigger, we do not have a horizontal asymptote. So that's some information about it already. Let's go ahead and start on our number line for the function itself. We're basically asking, where is this function equals 0? Now, of course, like I've said many times before, a fraction can only equal 0 if the numerator equals 0. Where is this quadratic equal to 0? Now, I don't really see a way to factor this, so we're going to actually use the quadratic formula to try to solve this equation. Remember, our quadratic formula goes negative b, so negative 4 plus or minus square root of b squared, so this 4 squared, minus 4 times a, which is 1, times c, which is 7, and then we divide by 2 times a, so 2 times 1. However, do note that what we get inside here, we get 16 minus 28. That is going to be a negative number. We get a negative under that square root. That means that this quadratic does not have any real solutions. No wonder you can't factor it. There is nothing to factor here. So we do not get anything for our number line based off of setting this equal to 0. Of course, we do need to include our discontinuity. We still need to include this negative 3. So this is for y. We still need to include that negative 3. We still go ahead and put in some test points. Now for negative infinity to negative 3, let's just go ahead and pick negative 4. If we put that into our function, this top becomes a 16 minus a 16 plus a 7. On the bottom, we have negative 4 plus 3 gives me a negative 1. So here we actually get a negative 7. We get a negative number. For the interval from negative 3 to infinity, we could just go ahead and pick negative 2. It is pretty close to negative 3. But I do want to know what the y-intercept is anyways. So let's just go ahead and pick 0. What is y of 0? What happens if we plug 0 into this function? Well, all the terms that have an x in them are gone. We just have the 7 and the 3. So we get a positive number there, and specifically we have a y-intercept of 0, 7/3. So it's negative here, positive here. So unlike the last two examples that we've done, we did not get a y-intercept at the origin. It is at a different point. Alright, now we need to look at the first derivative. So if y is equal to x squared plus 4x plus 7 over x plus 3, we need to differentiate that thing. We're going to have to use the quotient rule here. That means we differentiate the top. Derivative of x squared plus 4x plus 7 is 2x plus 4. We multiply that by the bottom, so we multiply it by x plus 3. Then we subtract the top as it originally is, times the derivative of the bottom. Well, the derivative of x plus 3 is simply 1. And then all this is over x plus 3 squared. I do want to simplify this because it's going to be pretty handy to have a simplified version of this for later. Plus, we're going to need to set this thing equal to 0 anyways. I'm going to expand this out. We get, and then subtract this. We don't have to worry about the 1 here, so we're really just subtracting these terms here. We have a 2x times an x, which is a 2x squared, but then we're going to subtract an x squared as well. So we're going to get a single x squared there. We're going to get 2x times 3 and a 4 times x. That's a 6x and a 4x, but we're subtracting a 4x as well. So we're only going to be left with that plus 6x. Finally, we have 4 times 3, give us a 12, but we're subtracting 7 from that, the 7 here. So we're only left with 5. And that's still over x plus 3 squared. Alright, so first things first, this derivative doesn't exist at negative 3. But we don't get a critical point there because negative 3 is not in the domain of the function. So we don't get any new critical points from having the derivative not exist. But we do get critical points from when the derivative equals 0, which of course just means that this top is equal to 0. This one can be factored. Actually, it just factors into x plus 5 and x plus 1. Because 5 times 1 is 5, but 5 plus 1 is 6. That means that x is going to be equal to negative 5 or negative 1. Those are going to be critical points. Or, well, yeah, I guess, yeah, they are going to be critical points for our function. So we're going to go ahead and make a number line for the derivative. We're still going to need to include that discontinuity at negative 3, but now we have points of negative 5 and negative 1 on either side of that to make a bigger number line. We're going to go ahead and pick test points. We're going to say y prime of, from negative infinity to negative 5, we can go ahead and pick negative 6. For negative 5 to negative 3, well, there's only one integer to work with, so we'll put a negative 4. From negative 3 to negative 1, we can go and just pick negative 2. And from negative 1 onward, well, 0 is probably the nicest number to pick. So let's go ahead and start with 0. If we plug 0 into here, the top just is reduced to a 5. The bottom is a 3 squared. So we have 5 over 9. It's a positive number. If we put in negative 6, well, here we have to kind of think about what it is. Well, plugging negative 6 in there was something we could do, but we also know that the numerator actually factors. We could plug negative 6 into here instead to get that numerator. So negative 6 plus 5 is a negative 1. Negative 6 plus 1 is a negative 5. And finally, negative 6 plus 3 is a negative 3, but that's squared. So we have 1, 2, 3, 4 different negatives. I mean, we could just write this as 5/9 if we want to, but it's a positive number, specifically what I'm saying. We have an even number of negatives. At negative 4, we can do kind of the same thing. We have negative 4 plus 5 is a positive 1. Negative 4 plus 1, put that in here, we get a negative 3. Negative 4 plus 3 gives us a negative 1, but it's squared. We end up with 3 different negatives. So we get a negative 3. And then finally at negative 2, plug it in here, we get 5 minus 2 gives me a 3. Negative 2 plus 1 gives me a negative 1. And then finally, negative 2 plus 3 gives me a 1 squared. This time we have a single negative, So we get a negative 3. Again, this is still negative. So we get positive, negative, negative, positive. Alright, one last thing. We need the second derivative. We're going to use our formula for the first derivative. And now we're going to differentiate it again. So it might seem a little much, but we can do it. We're going to use that quotient rule again. We're going to use the chain rule for differentiating the bottom. All that fun stuff. Derivative of the top, derivative of x squared plus 6x plus 5 is a 2x plus 6. We're going to multiply that by the bottom. We're going to subtract the top. And we're going to multiply that by the derivative of the bottom. This time we have something squared, so we're going to take that square and put it in front. We're going to take the something, but then we get to multiply it by the derivative of that something as well. The derivative of x plus 3 is just a 1. So this time it's a little simpler than it might have seemed. That's going to be over x plus 3 squared, then squared again to give a 4. And just like on the last example of our last video, we can do some simplification here because we use the chain rule instead of just trying to expand this thing out. Specifically, we have an x plus 3 here, we have 2 copies of x plus 3 here, and we have 4 copies of it down here. That means we can cancel a copy from each of these. And that's going to save us some work. So we don't have to take this times the square of something, we just get to FOIL this out. If we FOIL that out, we get a 2x times an x to get a 2x squared. We get a 2x times a 3 and a plus 6x. That's actually a 6x plus a 6x to get a 12x. We have a 6 times 3 to get plus 18. Here, well, the only thing that's left of this derivative back here is the 2, which we're going to have to distribute to both of those, all three of those terms. We get a minus 2x squared, we get a minus 12x, and we get a minus 10. Remember that negative there. All those need to be negative as well. Still over x plus 3 cubed. Of course, there's some cancellation that happened here. The 2x squared and the 2x squared cancel each other out. In fact, the 12x and the negative 12x cancel each other out too. We have an 18 minus a 10 to get just simply 8 over x plus 3 cubed. That is our second derivative. Maybe a lot nicer than you expected it to be. Now, we are asking, where is this second derivative equal to 0 and where does it not exist? Well, it doesn't exist at negative 3, of course. But that's a discontinuity. It's going to be on our number line, but we're not really including it as a potential inflection point. Also, this can't equal 0. If this was equal to 0, the numerator had to equal 0. But 8 is not 0. We have a constant on top. So this is actually doesn't give us any new piece of information. Not immediately. Our second derivative only has this negative 3 on it. But the fact that that's the only point on it is actually significant. We got that piece of information that there are no other places because we took that second derivative. We also can look at whether or not the second derivative is positive or negative by taking test points. Around negative 3, we can go ahead and find the second derivative, let's say at negative 4 and at negative 2. If we plug negative 4 into here, well, we still have an 8 on top. Negative 4 plus 3 is going to give me a negative 1, but it's cubed. The cube actually does not get rid of the negative. We get a negative 8 overall, so we get a negative number over here. For negative 2, we still have the 8 on top. This time we have a positive 1 cubed on the bottom, so we get a positive number. So that does tell us stuff about the concavity. We have the concave down over here and concave up over here. So we go ahead and sketch this thing. Actually, so I kind of drew this as if we were doing symmetric things on the other side of the axis. The fact that we have information about our function already tells us that a lot more stuff happens in the negative numbers. I probably shouldn't draw it like this. Should probably draw it with our y-axis a little bit more over here, because more fun stuff actually happens on this side of the axis. I'm going to go ahead and put in my vertical asymptote. Remember, that's at -3. Everything kind of happens around that, -3. So x equals -3. I know I have significant points at -5 and -1. I also know what my y-intercept is. If I go ahead and put in -1 into my function. Did I actually do that already? No, I didn't. We need to find out what y of -5 is. We need to find out what y of -1 is. So we're going to go ahead and plug those into our function. Yeah, we didn't actually call it f. It's just y of that. So at -1, so we have 1, the positive 1 minus a 4 plus a 7. That means we're going to have what? 8 minus 4 gives us a 4 on top. On the bottom, we have -1 plus 3, which gives us a 2. So we get 4. We end up with a 4 over 2, or 2 for -1. For -5, it's a little bit more work. We have a 25 minus 20 plus 7, so 5 plus 7 on top, or not, just a 12. On the bottom, we have -5 plus 3, which is a -2. So we're going to take 12 divided by -2. In other words, we're going to get a -6. So I'm going to have on here some points. At -1, I'm going to have a value of 2. At -5, I'm going to have a value of -6. And I'm positioning my labels here specifically because I know at -5, we do in fact have a local maximum. It was increasing and then decreasing. At -1, it's a local minimum. It is decreasing and then increasing. So my graph is going to have to be below this point, and it's going to have to be above this point. I also know that I hit 0 at 7/3. 7/3 is a little bit more than 2. It's actually a little, not much more than 2, but it is above 2. So we have a point like that. Our function has to be decreasing, or, well, sorry, it has to be negative. Everything is negative on this side of x equals -3, which already means that we definitely are going to -infinity on this side of this asymptote. But it has to be increasing until we get to -5 and decreasing after that. It has to be concave down. We got kind of a cup shape here. Or I keep switching those. It needs to be a cap shape. It has to go up to here and it has to go down to -infinity. On the other side of -3, it always has to be positive. It has to decrease, which definitely means that we are definitely coming from the positive infinity over here. It gets it to its local, or its relative minimum at -1, and then starts increasing, and it's always concave up, so it's always a cup shape. So it comes down here, bottoms out at that point, and ends up going up from there. And we get our graph. Got a good idea of what this looks like. Now, in this particular problem, there is actually something the book has not actually covered. If we go ahead and graph this, we can kind of get an idea of what the problem is. So remember here, y is equal to x squared plus 4x plus 7. We divide by x plus 3. We get this particular curve. Now, x equals -3 was our asymptote, our vertical asymptote. And so it kind of agrees with what we have. But what we did not find from this already is that there is another asymptote. It's not a horizontal one. This does not actually approach just a number as we go off to infinity. This has what we call a slant asymptote. This function, as we go to infinity or minus infinity, actually approaches the line y equals x plus 1. That is it is approaching that line. It's just at a slant. And none of our techniques that we've really talked about here do give us the insight on how that's true. But it does turn out to be true. It really boils down to the fact that if I use long division, if I start with my function x squared plus 4x plus 7 over x plus 3, I can use long division to actually show that this equals x plus 1 plus 4 over x plus 3. These are the same thing. And so basically, as we let x go off to infinity, this term here, the 4 over x plus 3, this is actually going to go to 0. And so as x goes off to infinity, this part becomes less and less significant. And so the function will start to look more and more just like the function x plus 1. It'll look more and more like y equals x plus 1. Same thing on the other end. If as we go to negative infinity, this still goes to 0, and so it's still going to look closer and closer like x plus 1. Now this actually happens because the degree of the top, this 2, was actually exactly 1 more than the degree of the bottom. But since our book doesn't actually bring this up, I'm not going to be saying anything more about slant asymptotes. I just wanted to say that all the techniques we have here are, while they give us a lot of information about a function, they might not give us every little bit. Not to discourage you or anything like that. We are getting a ton of information. We actually, even with the information that we had, we got something that is really pretty accurate in what we can see from here. Just maybe we didn't guess that, well, there is a line here that it approaches on either side. So hopefully at this point you can see how we're using these pieces of information. Of course, these are pretty long problems. I'm not going to assign a lot of them, but we do want to know how to do this. But that's going to do it for this section. I don't want to go through too many of these problems and just kind of overwhelm you with examples. But you should have enough information now to see what you're going to have to do on your homework problems. So I'll leave this for here and see you in the next section.